So, what could a sour lemon and a slippery bar of soap possibly have in common? Well, believe it or not, they're on opposite sides of a chemical battle that's happening all around us all the time. Today, we're going to decode the secrets of acids and bases, and you'll see just how much they shape everything from the food you eat to the supplies you clean with. Okay, so here's our game plan. We'll start by finding some common acids and bases that are probably already in your house. Then, we'll learn a super simple way to tell them apart, uncover their chemical secret, see what happens when they react, and finally figure out how to measure their strength. Let's get into it. First up, acids and bases around us. And believe me, we don't need a fancy lab for this first part. We're starting this investigation right in your kitchen. So, I'll ask you again. What do lemons, vinegar, and soap have in common? I mean, on the surface, they seem totally different. But chemically speaking, they're all part of these two big rival families, the acids and the bases. You know, our first clue actually comes from our own senses. On one side, you've got that sour pucker you get from an acid, like a lemon. On the other side, you've got that distinct kind of slippery feel of a base, like soap. Two completely different sensations, all thanks to their chemistry. And acids are absolutely everywhere in our food. That sharp tang in lemons, that's citric acid. The bite in vinegar, that's acetic acid. Even that subtle sourness you might find in buttermilk comes from lactic acid. They're basically nature's own flavor enhancers. Okay, so how do chemists tell all these things apart without having to taste them? I mean, that's not always a great idea. Well, let's look at a chemical detective's first tool, the simple litmus test. It's a really simple but kind of brilliant color change test. An acid will always turn blue litmus paper red. A base does the exact opposite, turning red litmus paper blue. And if you need a way to remember it, just think ABR, acid turns blue to red. Simple as that. All right, so we've identified them, but why does a lemon act like an acid and soap act like a base? What's the secret? To find out, we have to zoom in, like way, way in, to see what these things are doing at the molecular level when they dissolve in water. And here it is. This is the big secret. An acid's real power comes from one simple move. When it dissolves in water, it releases hydrogen ions. We call them H+. These tiny little particles are what give an acid all its special properties. Just look at this example. When a strong acid like hydrochloric acid, or HCl, hits the water, it basically splits apart. It lets go of its hydrogen, which becomes a free-floating H+ ion. And that, right there, is what makes the whole solution acidic. Now, let's check out the other side. A base that can dissolve in water is called an alkali. And just like an acid has its signature H+ ion, an alkali has its own secret weapon. So let's take sodium hydroxide, or NaOH. When it dissolves, it also splits up, but it releases a hydroxide ion, OH-. This is the calling card of an alkali. So the entire story of acids and bases really just boils down to this constant battle between H+ and OH- ions. Okay, now that we know their secret identities, let's get to the really cool stuff. What happens when these substances get to work and actually react with other materials? This is where the action is. First up, the pop test. If you've ever been in a chemistry class, you might have seen this. You mix a reactive metal like zinc with an acid, and it produces bubbles of hydrogen gas. If you collect that gas and bring a flame to it, you get that classic pop. That's the acid at work, freeing the hydrogen. Next, the fizz. Ever make one of those baking soda and vinegar volcanoes as a kid? Well, you were actually watching this exact reaction happen. Acids react with carbonates to release bubbles, and bubbles of carbon dioxide gas. This is also the same reason why acid rain can, over time, slowly dissolve marble statues. But what happens when an acid finally meets its opposite, an alkali? You might expect a big fight, but they actually neutralize each other. The H+ from the acid and the OH- from the alkali combine to form simple, stable water. And what's left over? A salt, just like the common table salt, NaCl, you might have in your kitchen. But, you know, not all acids or bases are created equal. Lemon juice isn't nearly as strong as, say, stomach acid. So how do we actually measure their strength?
Well, that brings us to the ultimate power meter, the pH scale.
This is the pH scale, and it runs from 0 to 14. It's really just a way to measure the concentration of those hydrogen ions we talked about. A low pH, like a 2 for lemon juice, means there are lots of H+ ions, so it's a strong acid. A high pH, like 13 for bleach, means it's a very strong base. And right there in the middle, at a perfect 7, that's pure neutral water. So when you think about it, this hidden battle between acids and bases isn't just for a chemistry lab. Their neutralization creates essential things, like salts, which are building blocks for both industry and for life itself. It kind of makes you look around and wonder, right? What else in your world is the product of a chemical war you never even knew was being fought?